This week we'll be covering Chapter 8, Bivariate Correlational Research. In this chapter, we're going to talk about relationships between two variables and how we can use correlational research designs to provide us with information about those relationships. This is the first chapter where we'll be discussing specific research practices and can be seen as a shift from more theory-oriented content to practical application of the material. This chapter is divided into two main parts. The first part is an introduction to bivariate correlations, where we'll discuss simply what they are and how they're performed, whereas the second part examines how claims associated with correlations are interrogated. We'll discuss how we can interrogate such claims using the same four validities we've discussed in previous chapters. So let's start off by talking a bit about simply what a bivariate correlation is. Bivariate, or two-variable, correlations are simply that, a correlation between two, and only two, variables. Bivariate correlations are also called bivariate associations. You can see here in the table on the right data from a study that examined well-being and deep talk. Here we see two variables being observed, individuals' well-being scores and the percentage of their conversations that were rated as deep talk. Just like that last table, here are two more tables from different studies that are looking at the relationship between two variables. It's important to note here that these studies may have asked more than just these two questions, but in a bivariate correlation, we're only selecting two variables of interest to examine at a time. Authors can investigate more than one correlation in a single study, however they must examine each set of relationships independently and report their outcomes separately. When we perform a bivariate correlation, we are necessarily looking at two variables. But what form those variables take will depend on what they are asking. For example, on the previous slide, one of the variables was a rating of marital satisfaction on a 7-point scale. Since this variable can range on a scale, it is considered a quantitative variable. It has a quantity of something that it is measuring. However, another variable measured was the location that people met their spouse, either online or offline. This variable isn't quantitative since it's not measuring some amount of something. Instead, it is what's called a categorical variable, as it simply measures what category a data point falls into. Next, we're going to discuss how we need to keep in mind what type of variables we have and how we would go about examining their relationships differently based on whether or not we are looking at two quantitative variables or if we have one or more variables that are categorical. Let's first discuss how we can examine associations between two quantitative variables. Here we have a graph of data points from one of the previous studies which examined the relationship between well-being scores and percentage of deep talk. We can see from the data, as well as the correlation line, that this relationship is positive, such that higher scores on well-being tend to be associated with higher percentages of deep talk. It turns out that the correlation coefficient R is equal to 0.28. Remember that R is a statistical value that represents the degree of association or correlation between two variables. Recall that it can range from -1 to +1, and that scores close to 0 indicate that there is no relationship between the two variables. Positive values of R indicate a positive relationship such that higher scores on one variable are associated with higher scores of another variable, as well as lower scores on one variable being associated with lower scores on the other. Whereas negative R values mean high scores on one variable are associated with low scores on the other. In order to determine the strength of the relationship, we should look at the R value. The closer it is to +1 or -1, the stronger the relationship. We can use Cohen's guidelines to evaluate the strength of such relationships based on R. You can see here the ranges for weak, moderate, and strong relationships. Based on this criteria, our relationship of R equals 0.28 would indicate a positive correlation with a moderate strength. We can look at another example here of a correlation between two quantitative variables. Here the two variables are representing multitasking ability, as measured by their O-span score, and frequency of media multitasking, or their MMI score. Is this correlation positive, negative, or is there no correlation? Well, it might be a bit difficult to tell, but it is in fact negative. Do you think the correlation is strong or weak? Well, since it's difficult to tell, it's most likely a weak correlation. The correlation coefficient, R, is actually negative 0.19. So, according to Cohen's guidelines, the association is small to medium in size. So in general, when we're looking at the relationship between two quantitative variables, we're going to be looking at the individual values of each data point. This can be depicted as a scatter plot, like what was just shown in these examples. We can then correlate these two variables and find a coefficient value, or R value, that tells us the direction and strength of the relationship. Next, let's talk about what changes when one of our variables is categorical. We'll first talk about the changes we'll see in the graphical form of our data representation, as well as how we can view and analyze our associations in a slightly different way. At the end of the day, it's important to remember, though, that as long as we are measuring the relationship between two variables, regardless of their type, we're still performing a correlational study. Remember back to the example of the comparison of marital satisfaction to the location where people met their spouse, either online or offline? Notice that the first variable, marital satisfaction, is quantitative, and the other variable, where a person met his or her spouse, is categorical. The graph on the left is a scatterplot representation of this data. Notice that since the bottom variable is categorical, our data points simply form two vertical lines. We can still perform a correlation on this data, however, and it turns out that we would get a correlation between these two variables of R equals 0.06, which is a fairly small correlation. It's much more common, though, to plot the results of an association between one quantitative variable and one categorical variable in a bar graph, like the one pictured on the right. In a bar graph, each individual is not represented by a data point. Instead, it shows the group mean, or average, for marital satisfaction for those who met their spouse online and the average for those who met their spouse offline. Here, the online mean is slightly higher than the offline mean, corresponding to a weak association between the two variables. Although it's possible to calculate an R value when at least one of your variables is categorical, it's more common to use a t-test to determine if the group means are statistically different from one another. Once again, a t-test would look at the averages between the two categorical groups and determine if one group was significantly higher or lower than the other group. An important point to note here is that t-tests can only compare two categories of a variable. So should your categorical variable contain more than two categories, you would need to use a more advanced statistical test, which we'll discuss in later chapters. So remember, association claims can be graphed using scatterplots or bar graphs, and they can be made using R or T tests. When making an association claim, the kind of graph you make or the kind of statistics you use aren't important. What is important is having two measured variables. Now let's shift to discussing how we go about interrogating association claims. Remember here, we're going to use the same four validities we've discussed in previous chapters to interrogate our claims. We'll talk about construct, statistical, internal, and external validity here. For association claims, the most important validities to consider are construct validity and statistical validity. Recall that construct validity is how well your variables measure the construct or idea that you are intending them to measure. It's important to consider the construct validity of both of the two variables in an association claim. You need to ask yourself, how well was each variable measured? Does it have good reliability? Did it measure what was intended to measure? And what evidence is there for its face, concurrent, discriminant, and convergent validities? When considering the statistical validity of an association claim, you need to consider the effect size and statistical significance of the relationships. Whether there are any outliers, was there a restriction of the range, and the possibility of a curvilinear relationship. Let's discuss in more detail each of these questions. Some associations are stronger than others, and the effect size describes the strength of the association. In the two graphs on the right, both associations are positive, but in graph B, there is a stronger association, or R is closer to 1, than in graph A. Therefore, B depicts a stronger effect size. You can also see the visual difference between the data points in the two graphs. Graph B has a more narrow band of points, which is how we can tell it has a stronger relationship than graph A, which has more spread out points. Once again, we use Cohen's guidelines for labeling effect size as small, medium, or large, based on our R value. Strong effect sizes enable more accurate predictions. The more strongly correlated two variables are, the more accurate our predictions can be. Both the scatterplots here depict positive correlations. Which scatterplot shows the stronger relationship? Well, graph A does. That means that we can make more accurate predictions from the data in graph A. In other words, we can more accurately predict an individual's score on one variable when given the score on the other variable. Conversely, we may make more prediction errors as associations become weaker, as in graph B. Both positive and negative associations can allow us to predict one variable when given the other variable, and the stronger the effect size, the more accurate our predictions will be. Effect sizes can also indicate the importance of a result. A larger effect size is usually considered more important than a small one, when all else is equal. However, there are some exceptions. Depending on the context, even a small effect size can be important. For example, in a medical study on heart attacks and taking aspirin, a small r of 0.03 was considered extremely important because of the number of lives saved. There were 22,000 participants in the study, 11,000 in the aspirin group, and 11,000 in the placebo group. It turned out that there were 85 fewer heart attacks in the aspirin group. That's a lot of lives saved for small effect size. But on the other hand, when the outcome isn't as extreme as life or death, then a small effect size might not be important. The next question we must ask ourselves in determining the statistical validity of an association claim is whether the correlation is statistically significant. Statistical significance refers to the conclusion researchers make regarding how probable it is that they would get a correlation of that size by chance, assuming that there is not a true correlation in the real world. The logic of statistical inference states that researchers collect data from a sample and make inferences to the population. Typically, what happens is the sample mirrors what is happening in the population, but this isn't always the case. If there's an association between two variables in the population, then there's usually an association in the sample as well. If there's no association between two variables in the population of interest, then there's probably no association in the sample. But sometimes, even if there isn't an association in the population, simply by chance there may be an association in the sample. Calculations of statistical significance help researchers evaluate the probability the result found in the sample match that of the population. So what does a statistically significant result mean? A probability estimate, or p-value, provides information about statistical significance by evaluating the probability that the association in the sample came from a population with an association of 0. If p is very small, less than 5%, then it's very unlikely that the results came from a 0 association. Thus, a finding of p of less than 0.05 is considered to be statistically significant. What does a non-significant result mean? If p is relatively high, greater than 0.05, then the result is non-significant, or not statistically significant. Therefore, we can't rule out the possibility that the result came from a 0 association population. Usually, the stronger a correlation, or the larger its effect size, the more likely it is that the correlation will be statistically significant. But we need to examine the p-value, which is dependent on both effect size and sample size. A very small effect might be statistically significant for a large sample, but not for a small sample. Small samples are more easily influenced by chance events than large samples. When we read reports of research or journal articles, there are simple ways in which we can quickly determine the statistical significance of the paper's results. Here's a table from a journal article, which contains a number of bivariate correlations. You can recognize statistically significant associations by their p-values. They will either be marked with an asterisk, with the term sig for significant, or with a p-value notation such as p is less than 0.05. A footnote explains what the asterisks mean. When interrogating association claims, we should always ask ourselves if there could be the possibility of an outlier. An outlier is an extreme score, or perhaps a few, that lies far away from the rest of the scores. The two scatter plots on the left are identical except for the outlier in the upper right-hand corner of the top scatter plot. The correlation coefficient for the top graph is 0.37, and for the bottom graph is only 0.26. Outliers can cause problems for association claims because they may exert a large amount of influence. In bivariate correlations, outliers are most problematic when they involve extreme scores on both variables. Outliers are most influential when the sample is small. The two scatter plots on the right once again are identical except for the outlier. Removing the outlier changes the correlation from 0.49 in the top graph to 0.15 in the bottom, which is a much bigger change than from 0.37 to 0.26 that you saw in the left-hand figures. So we can see from this example, outliers can have far-reaching effects on the conclusions we draw from our data. So again, it's important to consider the possibility of outliers and check in your own research to ensure that there are none. Should you come across an outlier, it's often reasonable to remove the data point or points to increase the accuracy of your analysis. We should also question whether there may be a restriction of range in our data. Restriction of range is when there is not a full range of scores on one of the variables in an association. A restriction of range can make the correlation appear smaller than it really is. If you look at the graph, you will see that the two variables are college grades, GPA, and SAT scores. The data are from a highly selective college that only admits students with high SAT scores. A plot of the correlation between college grades and SAT scores for students at this college yields a positive relationship, but the relationship doesn't appear to be very strong. However, SAT scores can range from 400 to 1600, but this particular college only admits students who score 1200 or higher. You can see this cutoff point in the vertical dotted line. Thus, the range is restricted to 1200 to 1600. If we extrapolate from the left scatter plot, we can see what the scatter plot would look like if the range was not restricted in the graph on the right. In the left scatter plot, r equals 0.33. In the right scatter plot, where the range is not restricted, the correlation is stronger, of a 0.57. So what can researchers do about restriction of range? Well, there are statistical techniques that allow correction for restriction of range. Or researchers can try to recruit more participants in order to widen the range. We may also want to ask if the relationship between our two variables might be curvilinear. A curvilinear association is one in which the correlation coefficient is 0 or close to 0, and the relationship between two variables isn't a straight line. Take this example. As people's age increases, their use of the healthcare system decreases. But as they approach 60 years of age and beyond, healthcare use increases again. The correlation coefficient is r of 0.01, which doesn't adequately capture the curvilinear nature of the relationship. However, the scatter plot can inform us about curvilinearity in cases where the correlation coefficient suggests that there is no correlation. Here, we can see that there appears to be a different pattern, a curved one. While I mentioned that construct validity and statistical validity were the most important to consider in association claims, it is still important to consider internal and external validity as well. Although it's not a priority to interrogate internal validity when making an association claim, we still want to consider internal validity because we want to be aware of the temptation to turn an association claim into a causal claim. One of the most important things to remember for association claims is that correlation does not mean causation. In order to make a causal claim, a study has to satisfy these three criteria. First, covariance. There must be an association between the cause variable A and the effect variable B. Second, temporal precedence, or the directionality problem. The causal variable A must come before the effect variable B in time. And finally, internal validity, or the third variable problem. Is there a third variable, C, that is associated with variables A and B independently? If so, then we can't infer causation. When we come up with a third variable explanation for an association, how do we know if it poses a problem for internal validity? Figure 8.16 shows a scatterplot depicting what the data would look like in Mel's study about deep talk and happiness if education was indeed the third variable responsible for the correlation between deep talk and happiness. Overall, there is a moderate, positive relationship between deep talk and happiness. But look what happens when we separate the participants into two subgroups based on education. The more educated participants are represented by green dots, and the less educated participants by blue dots. Notice that the more educated participants tend to score higher on both variables, and the less educated participants tend to score lower on both variables. If we look at the two subgroups separately, there is no positive association. Thus, the only reason deep talk and happiness are correlated is that well-educated people are higher on both of these variables. So education presents a third variable problem, and we refer to the relationship between deep talk and happiness as a spurious association, or one that is only present because of a third variable. The scatter plot on the right in figure 8.17 illustrates how the results could have come out differently. If you look at the red dots, more educated people, separately, you see that there is still a positive association between deep talk and happiness. If you look at only the blue dots, or less educated people, there is a positive correlation between deep talk and happiness still. Although level of education might be a third variable explanation for Mel's results, deep talk and happiness are nonetheless correlated within subgroups of more and less educated people. Thus, in this case, there is no internal validity problem. Finally, we should ask ourselves how important external validity is. Does the association generalize to other people, places, and times? It is important to note that the size of the sample does not matter as much as the way the sample is selected from the population of interest. If a bivariate correlational study fails to use a random sample, it should not cause us to automatically reject the association. Instead, we can accept the results as they are and save the question of generalizability for another study that tests the same variables in a different population. Also, many associations generalize to samples that are very different from the original sample. For example, in the scatter plot, older adults are represented by O's and college students are represented by Y's. Older adults might score lower on both variables than college students, but the same association might still exist within each group. When the relationship between two variables changes depending on the level of another variable, that other variable is called a moderator. For example, let's consider a study on the correlation between professional sports games attendance and the success of the team. Using data gathered over many Major League Baseball seasons, it was determined that in cities with high residential mobility, there is a positive correlation between success and attendance, indicating a fair weather fan base. In cities with low residential mobility, there is not a significant correlation between success and attendance. We say that the degree of residential mobility moderates the relationship between success and attendance. So we see that a city's degree of residential mobility moderates the relationship between local sports team success and attendance at games. Each dot represents one Major League Baseball season. The Arizona Diamondbacks are based in Phoenix, a city with high residential mobility. That pattern shows that people are more likely to attend games there when the team is having a winning season. Pittsburgh is a city with low residential mobility. That pattern shows that Pittsburgh Pirates fans attend games regardless of how winning the season is. So let's wrap up this week's topics. We first introduced bivariate correlations. We discussed how a bivariate correlation is simply an association between two variables. We talked about how we can use different representation and statistical analysis methods depending on whether or not we have a categorical variable. We also discussed how we would go about interrogating such association claims. We discussed what questions we might ask ourselves to determine the strength of the 4 big validities: construct, statistical, internal, and external validity.